Hello and welcome back to the lecture 6 of QM101. Today we will discuss further about the time evolution of in quantum mechanics, and we will also discuss the Schrodinger equation. Okay, we will see the form of Schrodinger equation. So let's get started. So in the last discussion, recall that we discussed that given a state vector which is defining the state at time t prime, as time moves forward, the state vector will change in general. Okay, so there were two point of views. In one point of view the state vector changed, other point of view the operator itself changed. So here we are taking the first point of view where the state vector change, which is the Schrodinger picture. So in the Schrodinger picture, the state vector which at time t prime will change to some time t as time elapses, and this time t, and since both of these vectors belong to the same Hilbert space, there is a map which we call time evolution operator, which takes one of these vectors to the other. So there is a vector at psi at t prime, you apply the time evolution operator which takes the state from t prime to t, and it will give you the state at time t. Now remember the principle of quantum mechanics, the fifth principle, which says that the time evolution of the state vector is unitary. And what do we mean by that? Unitary is this thing, that and the time evolution satisfies this equation. This is what we call unitarity condition. This is what we discussed in the last lecture. Okay, and what does this unitarity implies? It implies that the probability is conserved, or in a more abstract way, the norm of the vector. Norm basically means generalized length, the length of the vector, some general length. It's not the length which you can measure by a tape. Okay, so it's some general length, and that length is conserved. And it also means that you do not have to normalize your state vector every time you do time evolution, because if it is not unitary, then every time you do time evolution the length of the vector might change, and as you know, the length doesn't really matter here in this case. You can always multiply the state vector with a complex number and still get the same state. So the length of the state vector is not really what matters here. So we would like to keep it normalized as we move forward in time. Okay, so here today we'll discuss some further mathematical properties of this, not mathematical properties, the outcome of the mathematical properties that this time evolution operator has. So the first thing which you can see is that if the time evolution operator is taking from time t prime to t, and if you take the limit of this t going to t prime, that is, this is time t prime, this is time t, and you are taking the limit, you are making this go very close to this one. So in that case, when this is going very close to this one, it will basically be just the identity operator, because at time t prime the state vector would be this only. So when this has to be t prime, this operator has to be the identity vector. So in this limit, that time t tends to t prime, the operator from t prime to t, it tends to identity. Okay, so this is the case. Now what about when t is very close to t prime, say somewhere here where t is basically t prime, some t prime plus some small delta t. Delta t is like arbitrary small, that's infinitesimally small. Okay, in that case we can do a Taylor expansion. And now how can we do the Taylor expansion here? So what ensures that it's it satisfy all those functions, properties of all those functions all those properties of a function which is needed to do a Taylor expansion. So for that I would just say a few things. For most of the when we were learning this, what I heard that you just assume that it's a analytic in T and you just do a Taylor expansion. That's how we learned it. But I'll not just say that assume it analytic in time. I'll give you a rather hint toward the reason. I will not give you the exact reason, but a hint towards it, because the actual reason is much more mathematical and it's a little advanced stuff. So the notion of time evolution operators actually comes from something called it comes from something in concept of differential geometry. There you have the generator and all. Basically these things correspond to a Lie group, and there is a I think it was a bad idea. I think it was a bad idea to even point toward it, because it's actually really complicated. I'm not sure how to say it, but I can assure you that there's a mathematical reason why you writing it like this. Okay, so for now just believe it. Okay, and so we are writing it how we write Taylor series. That is when delta t is 0, that is it. In that point it will be identity plus some operator times delta t. This is the what we call the first order term, and delta t and this omega is something like the first time derivative. Okay, so generally this is how a Taylor series look like. F prime 0 x. So at x we have delta t at place of x, and the thing which is in front, that's minus I omega. This is something like this, f prime. So you can say it is something like the first time derivative of u. In fact, we will see the first time derivative of u further in this lecture. Okay, so now why have put this minus sign and this iota here? That will become like, it's just a mathematical convenience. It's not necessary, but it just gives this omega a meaning, which we will see later that what meaning it does give to omega. Okay, now assuming this form, and we know that the time evolution operator satisfies this unitarity condition, you plug it this expression here up to the first order, and then you do calculation. You just put it here, the identity, one identity, it will cancel out this identity, and you will be left at first order, you will be left with this thing, which eventually will give you that omega dagger is same as omega, that is omega is a Hermitian operator. Now see, we discussed Hermitian operator, and here we got our first Hermitian operator. Now what is this omega actually? So let's try to reason through it. There is no fundamental derivation from which you can derive omega. It is something which you give in the theory. It's something which is given in the theory. You postulate it basically, but there should be a reasoning why you are setting omega to be something. Okay, so let's see. So here notice again that here we have delta t, and what is the delta t is something which you can measure. It's a quantity, and it has the dimension of second. So, and I as it's a imaginary number, so it obviously doesn't have any dimension. So that means omega must also have a dimension, and that dimension should cancel out, because identity operator doesn't have any dimension. In fact, the operator doesn't have any dimension. So this entire term shouldn't have any dimension, but delta t has. So omega should have the inverse dimension, that is like inverse of the second. And what is that? Hertz, which is the dimension of frequency. So this omega is related to the frequency which we know, the normal frequency or the angular frequency. Generally this is more physical, but this is what we generally use in mathematics. Now, sorry, not in mathematics, in physics. And now you can see that, remember the Planck's law of quantum mechanics, sorry, not the quantum mechanics, the Planck's quantum law that says that the energy of a photon is related to its angular frequency. So the energy of photon is given by h cut omega or h bar. Some people call it h cut, some people call it h bar. You call it whatever you want, doesn't really matter. So from here you can write that omega is E over h bar. So this has dimension of this dimension which we need, hertz. Okay, so omega is something, and since omega is related to frequency, something like this or this, we just put it in the theory. Okay, this is a postulate of the theory. This was proposed by, I think, like the eventually you will get a Schrodinger equation from this, but I'm not really sure if he exactly proposed this formalism or somebody else did. Okay, but most likely somebody else did propose this formalism. So this omega operator, we put it equals to the Hamiltonian operator over h bar. And what is a Hamiltonian operator? Hamiltonian operator is the operator corresponding to the energy. Remember I told you that every measurable quantity has a corresponding operator. Position has position operator, momentum has momentum operator. Similarly, energy has energy we don't call it energy operator, we call it Hamiltonian operator. And the word Hamiltonian comes from the Hamiltonian mechanics, which is a formalism of classical mechanics. And Hamiltonian formalism is really important in the sense that Hamiltonian formalism directly translates from classical to quantum physics. Okay, we will also talk about that later in some video, not right now, maybe in some next 4 or 5 video. Okay, now we put this h hat to represent, this is notation to represent that it's a operator. You must have seen it in your school days, but later we will draw this hat symbol, but for now let's just keep it there. And once you put omega is equals to this, you can write the up to first order the time evolution operator as this, that operator which takes from time t to t plus delta t is identity minus I h cut over h cap over h cut delta t plus some higher order terms. Okay, now from this, given this, you can write, like, find how the state which is at time t moves to some time t plus delta t. That means you can get a small change in time using this operator. And how do you get a larger change in time? You just keep repeating this thing again and again. Okay, so you can repeat this small times. So it's like, how do you take how do you move a large distance? You can just take several small steps. It is just analogous to this, that you have a state at time t and you want to take it to some t, say letter t f, then you can just take small steps, delta t steps, until you reach that final time tf. Okay, now given this operator up to first order, you can write the time derivative of the state function. So we have state function psi t, and you take the time derivative. So what would be the time derivative? It is psi t plus delta t minus psi t divided by delta t. And this, since this is just psi t multiplied with the time evolution operator, you can write it like this, psi t here, and some operator which takes t from time t to t plus delta t minus the identity operator. Identity operator is sitting here basically, and you just take this thing and substitute it here, and you take the limit, then you will get this term minus IH Hamiltonian operator acting on psi t. And if you take this h and I on the right hand side, you get this equation. And this is what we call Schrodinger. This is the Schrodinger equation. I hope that you have seen Schrodinger equation before, but in case you not, this is how it looks, and it is the equation it is basically analogous of Newton's law for quantum physics. Okay, now some of you might be thinking that, okay, some of you who have seen Schrodinger equation before, they might be thinking, okay, this doesn't looks like the Schrodinger equation which I have seen. So for them I will just tell you, just wait for a while. This is the Schrodinger equation, but it takes the form of the Schrodinger equation which you have seen after some operation. Okay, so this is what I am telling you is the formalism of quantum mechanics which I am telling you, it is very formal, and a lot of textbooks and in lot of universities it doesn't start this way, the way I am going. Okay, So the equation which you have seen, we will come to that as well, but for now just remember that this is the Schrodinger equation, and this is Schrodinger equation for state vector. And that is how does the state vector change. Now you can write since the time dependence is there in the operator u itself, you can write the time derivative equation for u as well, and you just take the time derivative. You can write a differential equation for u as well, because the time dependence is coming from this part only. So you just take the time derivative here. Again, this thing you're taking from some time t prime to t plus delta t, and here from t prime to t. Now this thing you just take from t to t prime, and you take out the part. As I said, like, you can do it in successive operations. So you take up this part, you break it down from t prime to t, and then from t to delta t plus delta t. So t prime to t part will come out here, and you'll get this much. And again, putting this above form there and taking the limit, you'll get this quantity, that h operator is acting on u. So this is another form of Schrodinger equation, but this is for time evolution operator. Both of the forms are valid. You can just take the time, you can just, in fact, if you just see you can just multiply the psi there, so that will give you this equation. So both of these equations are Schrodinger equation, and both of them mean the same thing. They are just written differently for different objects, but they eventually mean the same thing only. Now this is the Schrodinger equation for time evolution operator. This is the Schrodinger equation for state vector. In books you will find both. In some books you will find this, in some books you will find this. So I'm just trying to cover both of them. This is taken from the book J.J. Sakurai, which is the most important book in quantum mechanics. But that is not for first time reader. I believe that for it is a little advanced, not very advanced, you can say intermediate level book. Okay. So in fact, a lot of my discussion of this lecture is from this book only. So if you want to read further, just check it out, this book. Now that we have a differential equation for this operator, and we are treating this operator like a function in time, because we wrote Taylor series and all. Now we would like to solve this equation and see the actual functional form of the time evolution operator. So our next task is to solve this for time evolution operator. Now we will not really solve it here, because it's an operator thing. So I'll not really do the complete solution here, and I don't think you will need that for now. So I'll just write the solutions, because this solution is what is more important. How does this time operator looks is more important, and you will use this time operator later in the problems. Now there can be multiple cases where you can solve this. Like, it's not a simple differential equation which you can just solve. There are several kind of scenarios where you have to solve it differently. So there are three broad cases. In the first case, we have Hamiltonian independent of time. That is, h doesn't varies with time, it just is as it is. In that case, the solution is very simple. You can just think of it you can just treat it like a differential equation of this kind. df by dx is equals to lambda fx. In this kind of equation, you have f of x is basically e power lambda x. This is the solution which you get. So it is the same kind of equation if you see, and the solution turns out to be this time operator, which is taken from 0 to t, or some ti to tf. The operator is exponential of minus I h t, and I'm dropping this hat from now on. I won't write hat operator, but you will I think it would be obvious that which is an operator and which is not. And in case it is not obvious what is an operator and what is not, I'll make sure that you understand, like I tell you that which is an operator and which is not. So this is a the solution IHT over H bar. Now what do we really mean by exponential of this operator H? Other things are number, that is fine, but what do we mean by the exponential of an operator? So you can define exponential of any operator. Say A is an operator, so you can just simply write it as Taylor series of exponential function, which is 1 plus a plus a square plus 1 by 3 a cube and so on. So this is how you can define the exponential of an operator. So this exponential is just this infinite series. Okay, and this is the solution for this Schrodinger equation when Hamiltonian is time independent. Now next case obviously would be time dependent, but there is a twist that along with time independent, it commutes, the Hamiltonian commutes at different time. And what does it mean by it commutes at different time? That is, since H is time dependent, you can write it at some HT, and the HT and HT1 and HT2, the commutator of these two is equals to 0. This is what we mean by when we say Hamiltonian, and let me just write it down, Hamiltonian at different time commutes. So this commutator being equal to 0 means that Hamiltonian different time commutes. And what is this commutator? For those who don't know, commutator is this thing. You basically they take two operators and say A and B, and you calculate this quantity, that is you act B first and then A later, and you take another term where you act A first and B later, and you take the difference of those two. So this quantity is called the commutator. And in this case, when H at different time commutes, in this case the time evolution operator would be simple integration of this Hamiltonian as a function of time with time from 0 to t, and this terms in front. So this is how the solution looks like in this second case. So here it is just multiplying the time here, the time difference from 0 to t, or from ti to tf. In that case it would be delta t, and here you are integrating over that. So it seems very intuitive as well. Well, it actually is, but except this part, that why is it necessary. And to be honest, even I'm not really sure why it is necessary, but I'm pretty sure that there must be a mathematical reason why this condition is imposed. And how this derivation is done, I'm not really sure, because I've directly taken it from a book. And as I said, this derivation is not that necessary for understanding quantum mechanics. Now the third and the last case, where the time Hamiltonian depends on time, and the Hamiltonian at different time doesn't commute. So this is a really scary situation, because it is the most general equation situation which you can see. And here, as you can see, I have written down the solution, that the time evolution operator is this infinite series. So if you cannot see, there is a dot dot dot, which means it's an infinite series. So first term is identity operator, then minus IH cut, then this integration term, something like this only. But here you notice that I have written the integration measure first, and it's a standard practice in advanced physics that you write the integral measure first, especially in field theory and Lagrangian mechanics and those things. Like, it is a standard practice to write that integral measure first, if you have not seen this before. And there's this second term that you take ht1 ht2, first integrate out t2 from 0 to t1, and then this quantity you integrate out the t1 from 0 to t, and you keep doing that for more and more terms. Like there will be 3 terms, h1 t1 h2 t3 and so on. So in general, the formula looks like this. This is how the nth term look like, minus I over h power and then integral 0 from tn. First you take integrate tn from 0 to tn minus 1, then tn minus 1 from 0 to tn minus 2, and so on up to you do until you get 0 from to t. And this is an infinite series, is what we call Dyson series. Now since it's an infinite series and you have to evaluate each term explicitly, this is not really used in quantum mechanics. Like, I mean, it can be used, but I have not really seen in the Schrodinger thing which we will gonna study in this course. But this is useful in quantum field theory, and this is the actually from where the Feynman diagrams, if you have heard about them, comes from. Okay, but I'll not talk about it in this course in QM101. Maybe if I haven't made a video on QFT, then in that maybe. And also in QFT we write this entire thing as a compact notation of the same thing which we write before, exponential and the integral of Hamiltonian, but with something called a time ordering operator. So again, this I haven't just taken from the book just for the completeness, but it's not really useful in here, so I'll not discuss this case. So but I just wanted to tell you that there are 3 possible cases for this equation, so you just don't think that there is only one, this or just this one. Okay, so with this I end this lecture. I hope you liked it. I was planning to keep it shorter, but again it took a lot of time because all these things were like, there was a lot of technical details. So I'll see you in the next video. And sorry for that background noise. So I was saying thank you for watching this video. Sorry, I was saying that after this one video I'll make one more theory video, I guess, and then after that we can do some examples, solve some problems. Okay, so stay tuned for the next video, and if you like this video, like the video, subscribe the channel for update on upcoming videos, and and have a good day, maybe, or a good night, whatever time it's there. See ya.